Welcome again for the second of my remote presentations. It's about a topic that I've already talked about a year ago, and it's something that's always sitting at the back of my head. And so whenever I have some spare time, I look at it again, and I think I've now converged to a good solution. So I would like this time to dig a little bit deeper into the implementation details to show you how all of this works and how this will look like once I polished up the paclet and made it available. So iterators, that's an interesting approach to computing with large amounts of data. Quite often you don't need to have all of the data available at the same time. You can work on it element by element. Think of mapping a function over a large list. No time do you need the whole list in front of you, and maybe you don't even need the whole result at the end. Or if you do something like select, then the result will be a lot shorter than the input. And for all of these situations, iterators are a way to save memory. It requires a different way of programming, which I will like to show you in this presentation. So iterators are representations of long lists where you never actually generate the whole list, but you just generate one element at a time, and then you work with one element. Functions like map and select are prime examples of this kind of list access. Also listable functions, member queue, that will simply iterate through the list until it finds the element it's looking for, or it falls off the end of the list. And so it may consume the whole iterator if the answer is negative. And to actually save memory, you need to be clever about these generators, these iterators, especially for combinatorial cases like all trees and things like that, which generate lots of output. There is literature about how to do this. And when you combine this with compilation, it can become quite efficient. Now, there are several ways to do this. There is the immutable way, sometimes called lazy lists, which I already presented a long time ago. It keeps being reinvented, so it's a very useful paradigm. And the one I'm exploring here is the kind of mutable list, where the iterator is an object which has internal state. So every time you request an element, its internal state changes and you cannot go back. Each of these has its advantages and disadvantages. So really there's no good reason to just use only one or the other. Now there are related concepts. There are the notion of out-of-core data, where you don't need to bring the whole data into your process. So the idea is very similar. You work at it one piece at a time. There's things like sow and reap, which build the results as they are found. There's cloud expression, where the whole computation is relocated to the cloud and the data never leaves the cloud, even though you do computations with it. Or there's the notion of a coroutine, which is a separate process. For example, assume you have a process that generates all binary trees. As soon as it finds one, you can stop that process and work with that result it found, and then you let it continue. So you don't need to program all of the stack and everything yourself if you have the coroutines available in your system. So I'll talk about the minimum requirement for mutable iterators, then quickly talk about the framework for iterator factories. I'm not going to spend a lot of time on this because I explained that in detail last time, and that this particular part of the code hasn't changed. We'll talk about operations on iterators and how to turn them into a native data type in the Wolfram language. So this code will soon be available in the paclet repository. There's a version there from the spring which behaves similarly, but it's older code, and I haven't had the time to update the code and publish it in a new version. So the main point I want to make here is that you don't need a full object-oriented language or full-blown system for working with iterators. You can just handcraft an iterator. Now, an iterator needs something, a handle under which you work with it. And so in this case, I create a symbol in module. I attach definitions to that symbol, and then I return that symbol. So this symbol is now an iterator because it knows one method, how to get the next element, and it satisfies the iterator queue predicate. The iterator has internal state, so I need another local variable that I initialize to the value before the intended first value. So if I want the integers from 1 to infinity, then I initialize that to 1. And so here is my iterator. It doesn't look like much, right? I mean, it's completely opaque. You could, of course, dissect it, but that's really not necessary. So every time you call this iterator, it will give you the next value. So next 10 values and so on. And it is an iterator, so all the support code knows that it satisfies the predicate. So let me go back quickly. So how does this work? Well, the idea is that you don't need to specify a whole class hierarchy of iterators. All you need to do is to figure out exactly what does it mean to be an iterator? What does an iterator need to provide? And that there is very little that it needs to provide. Essentially, all it needs is a method, a function that delivers the next element, and that modifies the internal state. And then, of course, you need to recognize it as an iterator, so the support code knows that this is a valid iterator, so you need a predicate. Now, this iterator doesn't have any of the fancy stuff that you sometimes see. It doesn't have a peak method. It doesn't allow you to reset its state. It cannot be cloned, cannot be destroyed, and so on. But for many applications, this is good enough. So really, there is only this next element function. Now, there is another thing that you frequently need. I didn't need it in this example because I chose an infinite iterator that never runs out of elements. And of course, you can also work with finite iterators. And then you need to tell the function that gives the next element needs a way to handle that exception when there is no next element. And there are really two ways to do this. Either you return some error value, or you generate an exception. Now, if you think of something you're probably familiar with, and that is the readline function that reads lines of a file. This is, you can think of this as an iterator. Every time you invoke it, you get the next line of a file. But eventually the file is finite, so eventually the file will run out of lines. And then that function will return a special value, end of file. And you can write an if statement that tests whether the return value is that special symbol. This is easy to use interactively, but when you program, you really don't want to use these error values because you always need these if statements, and then you need to propagate the error, and so it quite quickly becomes messy. So for programming, exceptions are much easier to deal with. So what I've decided that this iterator interface will require a specific exception to be thrown when the iterator runs out of values. Now, later on, you will see that I will actually intercept this exception. And so if you use it interactively, you will not see that ugly uncaught exception. So I've then decided not to become too fancy, no peak, no empty queue, no set, reset methods. just a very bare minimum. Now, there are some optional additional methods that are quite useful, but they are strictly optional. Sometimes you know how big your iterator is, so a method called size that returns the number of remaining elements is sometimes useful, and a constructor that gives you the function call that you would have to use to create a copy of the iterator is also very useful because it allows you to clone iterators. Iterators are mutable, so every time you ask for an element, it is modified. So the iterator in a way destroys itself. And so you need a way to create independent copies of these mutable data. And that is what cloning is for. And I will show you how this works. Now, before I've created a single handcrafted iterator. That is fine, but that is, of course, very cumbersome. Now, if I need many iterators with arithmetic progressions of the positive integers, then it makes sense to write a method that creates iterators. Now, the iterators that it creates uses the same idea as before. It creates a symbol and it attaches definitions to those symbols. This is exactly the same as before, but I've packaged everything in a function called makeRange that takes the same arguments as the built-in range function. And it also implements that optional size method. And so this is, of course, a lot easier to use if you do it this way. Then you don't have to write this every time you create an iterator. So here's an example. Odd integers starting with 1. It's obviously infinite because the upper bound is infinity. And the first one is 1, 3, 5, and so on. Now here is a different approach. Satisfies the same interface as before. So you can mix and match these as you like. This is more like traditional Lisp, but mutable, if there is such a thing. So I use the mlist as a constructor and as a data type. So the idea is that you turn an ordinary list into an iterator. So it needs internal state. So I create a symbol and then I store that symbol unevaluated inside the data type. So that is the constructor. And these are the methods. So the next element function call operator. And here you can see that obviously this list will eventually run out. So if it is the empty list, then I raise this exception. Otherwise, I turn the crank and advance the list by 1 element by setting the rest to be the rest of the previous value and the size. And here I also give a constructor. How do you construct a copy of the current list? Well, you have to evaluate that hidden variable and call the constructor with that list, but you have to wrap it in hold, otherwise it would create it right away. So I don't want to create a copy right away. I want to get a hold of the constructor call itself. And I've also added a little format so it looks nicer. So let's see what we can do with this. So here I create an iterator form of this 4-element list. Every time you ask for an element, it gives you one. Here is the constructor. You see it inserted the current state of the iterator. And if you now do release hold, you have a clone of the original list. And the built-in clone function does nothing else but release hold of constructor. So now I have 2 independent lists. Both my list and my list 2 can run independently. Now you need cloning if you provide iterators as arguments of other functions and you don't want to consume the argument, or you use this form. This is also a very useful form for serializing iterators. you can write this to disk, you can send it over mass link to remote processes, and so on. So this cloning and constructor is a very useful concept. Now, typically when you talk about an interface, and I use this word in the Java sense, an interface is a collection of requirements that piece of code needs to satisfy so that you can use it interchangeably with any other piece of code that satisfies the same interface. Now, typically interfaces don't have code, they just have method declarations. But if you think of it a little bit differently as an abstract base class, then it makes a lot of sense to provide code for all of these things that do not depend on the representation of your data, so-called generic methods. And you also can provide defaults for the pure virtual methods, as they are sometimes called. So if an iterator doesn't specify the size method, I will simply say it's indeterminate. And here is the clone method that we used before. And the constructor, by default, there is no constructor. So if you call the constructor on an iterator that doesn't define one, it raises this error. And so this is really all there was for the examples we've done so far. So this again goes to avoid repetition of code. But you can do more. Many of the functions on iterators do not depend on the representation. Essentially, excuse me. Essentially, if you don't need to create a new iterator, then you should be able to express your code independent of the implementation. And so to make that work, the interface also provides default implementations for many useful functions. So here are some examples, and they show you how you typically program with iterator. Well, here's a function that gives the first element of an iterator. Now, it's of course the first element is you just call the next element method. No, this is just a wrapper at the moment. This doesn't seem particularly useful, but it will become later on because we can then overload the system function first. So that first can work on iterators and you don't even notice that you have an iterator inside. But of course, this iterator might not have a first element if it doesn't have any elements at all. And so this would then generate an exception. And here I catch or handle the exception. And if that happens, I then create a failure object that tells me that this iterator doesn't have a first element. Same with the REST function. This is actually somewhat special, that there really is no need for a REST function, because once you ask for the first element, the iterator mutates and it becomes its own REST. So there's really nothing to do. It's just, again, a convenient last element. That is more interesting. Well, what do you do to find the last element? You just call the next element function until there's nothing left, and you generate this exception. And when the exception happens, then you return the element that you remembered from the previous invocation, except for the special case when there are no elements at all. Then of course there's nothing you can do, and so there's this special tag that you can then use. And so if the iterator doesn't have any elements, then it doesn't have a last element. Now this is a useful function, normal, which turns an iterator into a list. And this is essentially the same. You have while true, you go through the iterator, and every time you find an element, you remember it. And so there's this reap and sow, which is very useful in this particular case. And here's the other member queue, which is a useful function. So again, this iterates until it finds the element or it falls off the end. And if it falls off the end, then the exception handler returns false, otherwise you return true. So these are all completely generic implementations. There's nothing that depends on the implementation of the iterator. So let's see how this works. So I create this. So I call the first element, the rest, then the fifth element, take the first 10, check whether 99 is a member of the odd numbers. Yes, it is. And here I check whether 100 is a member of the odd functions, and it's still running. Maybe you can see it up here. It will never finish, of course, because it doesn't know that it has overshot, and so I have to hit Command period to abort this. Now, this is a consequence of the fact that with infinite data types, some operations are partial and they may not finish. So without additional knowledge, I have no way of knowing that this will never return true. Here's an example using that mlist constructor. Scan works, fold works, and so on. So essentially any function that takes a list as argument in a certain element by element way is a candidate for turning into an iterator function. Now, this is something I talked about at length last time, so we'll go through it quickly. We have seen how we can write this factory for range iterators, but that by itself had a lot of boilerplate code. So there's even a step further I can take. I can write a factory method that declare iterator that makes it easy to declare different iterator factories by providing all of the standard code automatically. So if you do it this way, then we declare iterator. Here's the name of the iterator. Here's the list of instance variables. Here is the pattern for the constructor. Here is the next element function. Here is the size function. And so the syntax looks easier to use because you can declare these variables. You can use these variables directly. But believe me, that was not easy to do because you have to write rules that modify patterns and other rules. So this code is quite hairy, but it works well. So declarations, the name of the iterator, the list of instance variable methods, and so on. So really, it's supposed to be easy to read. And so if you do this, and I should have evaluated that. So now I have a new iterator factory called my range. And now I can use that. So here are the negative numbers, and there are infinitely many, the first 10, and so on. So now it really becomes easy to write new iterator factories. I don't want to talk in greater detail about the constructor definitions. Essentially, the constructor either calls itself with additional arguments. That's useful for providing defaults, or there's one rule that actually has to initialize all the instance variables. So that's the main job of the constructor, is to initialize all the instance variables. Now, if you feel like you can look at the implementation, so you can see here are the instance variables. These are the per iterator versions. So each iterator obviously has its own copy of these variables, but you never need to see those. You never need to type this. You can just use the standard name here. The method definitions, they look like ordinary function definitions, but actually this pattern must have one of these two forms. It is not used like that because that would match everything, including syntactically wrong cases. So there's actually a lot of trickery going on behind the scenes. So now what can we do with these iterators now that we know how to create them? So there are really two cases. Functions that consume the input iterator. We've already seen some of those, and that return a single result. And then there are, of course, functions that take an iterator's argument and return a new one. And so this is how you can build up more complicated cases. Here is the most important one of those, map. Map is intended to work just like the standard function map. It takes a function as argument, and then it takes an iterator as argument instead of a list. And so it has to create a new iterator whose elements would be the elements of the original one, each one wrapped with a function f. So really, it's very easy to do. You call the original iterator, which is an instance variable. You apply the function, and the result is the next element of the mapped iterator. And the length of the mapped iterator is, of course, the same as the one of the input elements constructor. How do you clone the map? Well, you first have to clone the input iterator, so it becomes independent, and then you just call a new mymap constructor. Now, there's one thing conspicuously absent. Now, this input iterator may run out of elements, so it would generate the end of iterator exception. But if the input iterator runs out of element, then so does the mapped iterator. And so I don't even have to mention that condition. I simply let the exception escape to the outside. I mean, this is the main reason I like to work with exceptions, because in many cases you don't even have to deal explicitly with these error conditions. No if statements, no nothing. I mean, just imagine how complicated it would become if I had to test the return value of this, and then if it is end of iterator, I would have to return that, and so on. So this is really a good case strong case for working with exceptions. So here is an example. I take my ranges of integers and I map squaring function. And so here are the first 10 squares, of course, infinitely many. But now see that the input iterator, which I gave here as argument, has been consumed because it is mutable and there is no independent copy made automatically. That is by design. So quite often that's okay, but if it's not, then you have to clone the input iterator. So now it's time to talk a little bit about cloning these iterators. Now, in this particular case where you specify a brand new iterator as argument, there's no reason to clone because you don't use it outside. But of course, if your argument is another iterator, then you better leave it alone, and then you should clone it before calling the map function. So if you do that, if you clone it, then you see the input has not been modified yet, even though I've taken off 10 of its elements, because that also worked on the clone. So this is the effect of cloning of the argument iterators. And we've already seen how we do this. We take the constructor and we call release hold, and that is essentially the cloning method. Now, of course, you have to also clone the argument iterator if you make a clone of the mapped iterator. Otherwise, you would run into the same problem that the two are not independent. And so there is this auxiliary function for creating a held clone inside the held constructor. I'm also not going to talk about compilation because I didn't actually. Originally I planned to show some of the compiled iterators, but due to the imminent release of the next version, 13.2, I was rather busy with fixing bugs and making improvements to my parallel code that is in the system. So I didn't get as far as I wanted to. I will eventually write this up separately, because this is quite an exciting topic. Because if you think of an iterator for all the binary trees, now if that can become, if you can write this in compiled code, it will become very efficient, just like our built-in compiled data structures. I mean, an iterator is a data structure, though I can use the same functionality there. And then you would have a high performance iterator or loop over binary trees or other large combinatorial spaces. And that is really where iterators shine, because you don't have to generate all of these millions of trees with certain symbols all at the same time. Especially also if you then want to parallelize your code, you don't need to send those millions of trees to your parallel kernels. You just send the iterator constructor calls to all these kernels, and they will then generate their own independent copies. So this is an exciting thing to do. I mean, this particular example just uses a data structure as a way to implement an iterator. So before I go on, let me quickly recap where we are now. I started with simple ad hoc iterator definitions, set up the requirements for iterators, the so-called interface. Then I talked about generic functions, generic operations that you can do independently of the implementation. And then we provided a way to easily write iterator factories for different types of iterators. This is all nice, but to really use that, it would be nice if we could just use iterators wherever we have ordinary lists in all the built-in functions. Map takes a list as argument. Why can't it take an iterator? Same for select, fold list, prepend, append, all the element extraction functions. Iterators, well, in a different sense of the word, a table can have a list as its iterator. Why can't it have an iterator as its iterator? Member queue, free queue, these are all also sorts of loops. Then there are all the accumulators, scan, fold, total, max, all functions that consume the whole input. And then in the second step, we can examine all the functions that generate lists and see whether they could generate iterators instead. We've also already seen range as my main example for an iterator factory. But there are others. There's constant array, there's nest list, which creates a list, and so why can't it create an iterator? Then there are all the important combinatorial generators, groupings, permutations, and so on. Read list, why can't you attach an external file to an iterator and read it line by line like this? Random number generators are also good sources for iterators. List itself, any list could be turned into an iterator. And of course, our data structures as well. So how do we go about designing an easy-to-use system for this? One way to do it would be just to have functions: iterator map, iterator select, iterator prepend, iterator table. Then we've already have I range, I read list, I constant array, and so on. But then, of course, you just create lots of new symbols that really do the same thing. Now, we've always had a system which is polymorphic, so we can easily extend that polymorphism. So we can use the standard map function and simply make a second definition, so that map, when its second argument is an iterator, will call our code. That is actually surprisingly easy. I've already done that last time, so this is kind of a recap of some of the capabilities, and this time I'm going to show you a little bit more of how it is actually done. So the goal was to use existing function names for the constructors: range, nest list, list, random real. Make the existing functions that operate on lists also operate on iterators. And that was actually quite easy thanks to the polymorphic design and up values and things like that that you use here. So let's look a little bit at how this actually works. Now there's another thing. Well, the first ingredient is a data type for iterators. So far we only have an interface. So we have our raw iterator, but there is no data type for iterators on purpose. I didn't want to restrict iterators to single data type. So let's just create a generic data type called iterator object, and it accepts anything that satisfies the iterator queue predicate, and it wraps it. It produces a nice standard form. You are familiar with this kind of presentation of objects, which show you the type of the thing and icon and some information about it. And the benefit of doing it is that I can now overload all desired system functions to work on this data type. So I can ask for the length of this thing. And I can also overload all listable arithmetic functions. So I can take my iterator, square it, element by element, and I add 1. That gives me another iterator, and here are the first 10 elements of it. Or I take my iterators and select those that are prime. That gives me another iterator. And here are the first primes from this particular iterator. So I can just pretend that these arguments here are lists, and it all works. And in particular, it would also work with your ad hoc iterator that you created, that I created a long time ago. There's nothing magic about this. It doesn't require the use of this iterator factory that I presented before. Anything that satisfies the interface will automatically work. So how does that work? Well, here is the main constructor for the iterator object. It simply says, if my argument is not an iterator, then I complain loudly. Otherwise, I don't have to do anything. I don't do anything. I just keep it wrapped inside the iterator object. So now I know that every iterator object that you see in the wild actually contains a valid iterator inside. And so here is the next element function applied to iterator objects. And principle is always the same, of course. You extract the inner iterator, you call its next element function, then you in this, and then here comes the neat thing. You turn the exception that happens if it becomes empty into that end of iterator symbol. So here is the convenience, the interface between the low-level code that works with exceptions and the high-level interactive code that you may use directly in a notebook, where you don't want to see exceptions that have not been handled. So you simply return that symbol. And what is the length of an iterator object? Again, you extract the iterator, call its size method, and then that's the result. The constructor is the same. You extract this element, you call its constructor, and then you have to reinsert the iterator object inside. So it's a little bit complicated here, but really, I mean, just one line of code for each function that we want to support. So here is the first element of an iterator object where this generic function it_first that I talked about comes in handy. Here is map. Map calls my code from the iterator library and just wraps it again with iterator object. So it's really surprisingly easy. There is usually one line of code and usually an up value on iterator object. So technically, I'm not even modifying built-in system functions. I just extend their domain by providing up values. Now there's one last design problem. Now remember we had things like I range of 10 or so. Oops. Oh yeah, here it goes. And I could of course wrap this in iterator object. Oh, there is something. Oh yeah, oh here it is. Okay. So now I have a valid iterator object and I can ask for its next element, right? So, but I would still have to remember all of these names for all the constructors. And so I thought, well, why do I have to remember new names? Why not take the existing range function? And so here is a wrapper iterator that takes an unevaluated function call. And if it is one of those for which there is an iterator, it would simply call that function and everything works as before. Now, this is a bit controversial because how do you know which ones work, right? If I say iterator of, I don't know, what is a good function on array of, let's make a simple example, array of some function on 10. Well, no, it's not recognized as a valid constructor. So you still need to know which ones work, and so you could argue that maybe you shouldn't do this. You should just work with names like iterator range, and then you could ask for iterator star and see which ones exist. So I'm not completely sold on this. It seems useful in this particular case. Of course, you still need a list of those that are supported. And another minor criticism is that, of course, the argument structure of this iterator version is different than the one in the system. I mean, here's an example: iterator of nest list f on 0. You see, the nest list takes a third argument, which is the number of nestings you want. But here, of course, I want infinitely many, so I don't bother to say so. So this also works with a different default for the third argument. So that's, I understand the criticism, and so maybe we'll end up doing something differently in the future. Now here's another simple case: take a list and turn it into an iterator version of itself and ask for its last element. Now, how does this work? Well, this is just can probably guess how it works. I have lots of rules like this. These are not up values. These are rules for the iterator auxiliary function. And so it's just a big list of pattern matching. If the argument is of the correct form, I know which iterator to create, and then I wrap it in iterator form. So this is, again, very easy to implement. All of this code will be in a paclet. So let me quickly show you some of the software engineering behind these packlets. So this is how the paclet looks like, and it defines code and it defines a startup file. Now, simple packlets figure out the auto-loading and everything automatically. Now, this is a little bit more complicated. So I have explicit declare load statements in that startup code. And here it specifies hidden contexts, so you still need to say needs iterator interface to use that, except of course for the main code for the system integration where I export the context. And so it will show up. So by now, of course, we have more no context paths, I wanted to say. So by default, only iterators will be on the context path. These are the ones you need if you program, if you create your own iterators. If you just want to use iterators, you don't need that. Then this is all you need, and that will be on the path by default. So as I said, it will become available in the paclet repository. At the moment, there's only version 2 there, which behaves similarly at top level, but there are some significant changes under the hood. Well, no talk of mine would be complete without something parallel. So on the other hand, iterators are by definition sequential. So because you only get one element at a time, so it's kind of difficult even to distribute them to parallel kernels and work with them. But there are still some useful operations that benefit from parallelism. One of those is select. Now select sometimes has to examine lots of cases until it finds one where the predicate returns true. And so it is a candidate for parallelism. Now you have to be a little bit careful how you write that parallelism. So here you will see lots of queue management code. So what happens is if I ask for the next element, then the whole big program starts to run. And I keep a queue of cases that I've already submitted to remote kernels. And if that queue becomes too small, I submit additional cases. And then I have to wait for one of them to finish. And if that one returns a true result, then I'm done for the moment. And I return that result as the next value of the iterator. Otherwise, you see there's a big while true loop here. So I will have to keep running until I find a case that matches. And of course, it may happen that the iterator runs out of elements before there's one that matches. And so this is a bit complicated, but it's typical of those kind of search loops that you want to parallelize. For parallelizing search loops, it's often better to use the parallel submit and wait next paradigm rather than things like parallel map or parallel evaluate. So while this code is complicated, it follows standard queuing paradigms for parallel submission. And so let me show you how this works. So let me launch my kernels here. And while I do so, I start with the positive integers, and I want to find integers such that 2 to the prime I minus 1 is prime. So these are the Fermat primes. And so here is the first one. And I should have said that, sorry, let me go back here. I did define one additional method for my iterator. Nothing prevents you from writing your own, adding your own methods. They will simply be part of the that iterator definition. What I want to do here is I want to see how the queuing works. So this is a kind of a debugging method that returns information about the queue. So let me, if I can somehow go to the next slide. So queue length now shows me I have 88 kernels, so my queue has length 89, so that's 2, and 2 results have already returned. So if we take the next 16 Fermat primes, it should hopefully not take too long. And the next one, actually, the next one And the next one that came quickly because it was already computed, because I have 88 of these kernels. Now there's one more thing that it's for the first time you have to be careful about this. And when you have data with built in with state, so mutable objects, you have to think about memory management and destructor calls. And here, of course, I have a whole parallel computation running in the background, so it would be rather bad if I just threw this away without cleaning up. So there is support for a destructor call for iterators delete object, and this one takes care of training the queues, resetting all the kernels, and becoming ready for the next computation. Now, this is the price you pay for some of these mutable data types, that you need to do some some memory management yourself. So I thought there was a last slide. So this was the last slide. So I gave you an update on my progress with this iterator project. I think it's now ready to go into to be published as a near final version. I've sorted out all the internal details of the interface and the generic code, and I didn't have to do a lot with the iterator factory. That worked very well. And I also showed you how you can write your own minimal iterators and how you can even do parallel programming with iterators. And with that, I would like to thank you for your attention, and I'm available for questions.
So I had a question. So the construction of that head, you can define that in a way to where every time that you encounter that on the input to a function, you can guarantee the form of the contents and essentially just check for the head as opposed to doing a form checking on the inputs of the function.
You're talking about iterator object?
Yeah.
Okay, yes, here. Yes. Yes, so iterator object is just like the mlist before. It's kind of like the built-in association. It serves a dual purpose. It is its own constructor, right? You write association of something to create an association, and the result has the same head, but it has certain validity criteria. And this is a simple way to guarantee that, because I don't have a single data type hierarchy, so I need to use a predicate for determining the validity. And that's why I simply say I never want to see an iterator object that contains anything other than a valid iterator. And then I don't need to do any argument checking on any functions that use iterator object, because I know what's inside.
And is that something that is common across other data types in Mathematica?
Good question. Now it's something, something I've used a lot. For example, the persistence locations that you may have run across with the initialization system work in the same way. They are their own constructor, and they are very careful of turning into $failed if the structure is not correct. I find this easier than having to put, it essentially means I test once, and then the system has certain optimizations that it never has to retest that once the predicate turned into true. And so I think it is, if it's possible to do so, it is a good way to implement data types which are their own constructor. Whether you want to do that, of course, I could have say something like make iterator object. That would then do a lot of validation, and then return an iterator object as a result. But I didn't think it was necessary here, because I quite like this approach here.
Thank you.